This video is part 1 of a final preparation session that I did for my Year 12s ready for AQA AS-Chemistry Paper 1. Because PowerPoint won't let me export a video longer than an hour, I had to split the video in two, so this is just the physical chemistry topics. Make sure you also watch part 2 for all the inorganic material. If you used my final preparation videos for GCSE revision, then you may be surprised by how much I'm skimming through some of the detail here, but AS Chemistry is obviously a lot bigger than GCSE Chemistry was, and so I can't fit in the same level of detail. Having said that, I have covered every part of the spec, and I've tried to give some pointers and reminders of the most common places that students tend to trip up in exams and lose easy marks. The first topic in Year 12 physical chemistry was atomic structure, and a lot of this was very familiar from GCSE. You should know that an atom consists of a nucleus containing protons and neutrons, and we call those particles nucleons, and they're surrounded by electrons. The absolute masses and charges of the subatomic particles are incredibly small, so rather than referring to those actual numbers, we tend to talk in terms of atomic mass units and atomic charge units. So an atomic mass unit is 1/12 of the mass of one atom of the carbon-12 isotope. You need to appreciate that knowledge and understanding of atomic structure has evolved over time. So this hasn't come up a huge amount, but in 2018 we were asked about differences between the modern model and Thomson's plum pudding model. So you should be aware that that has no nucleus and the electrons are not in shells, they're just scattered throughout the atom. And then in 2021 we were asked about Rutherford's nuclear model. So this doesn't include protons and neutrons, it just has one undifferentiated nucleus, and then the electrons are not separated out into different energy levels or shells. Atoms are classified as belonging to a particular element based on the number of protons they have. So any atom with one proton is always hydrogen, 2 protons is helium, and so on and so forth. The number of protons is called the atomic number, and that has the symbol Z because of the German word Zahl, meaning number. The sum of protons and neutrons in the nucleus of an atom is its mass number, and that's A. And mass number is always going to be an integer because for one particular atom, the number of protons and neutrons is always going to be a whole number. For any given particle, you need to be able to identify the number of each subatomic particle. So for instance, here we're given 48 titanium 3+, so you could look at your periodic table and see that because it's titanium, it's always going to have 22 protons. And then in order to work out the number of electrons, of course, we need to look at the charge. Here it's a 3+ charge, so we're expecting 3 fewer electrons, so that's going to be 19. And then finally, we use the mass number to work out the number of neutrons. And remember, it's the mass number of this particular isotope. It's not necessarily the same one that you're seeing on the periodic table, because that's the relative atomic mass. So here it's 48, take away 22, it would be 26. Isotopes are different atoms of the same element, and therefore they have the same number of protons, but they have different numbers of neutrons. They're chemically identical, in other words, they undergo exactly the same chemical reactions because they have the same electron configuration. But they're physically different because they have different numbers of neutrons, so they may have different melting points, radioactivities, and densities. Unlike mass number, which is for one particular atom, relative atomic mass is a figure which takes into account all of the different isotopes of an element, whether that's in the whole world or just in a particular sample that we're looking at, and also their relative abundances. So if we have a lot of a particular isotope, then it makes up a greater proportion of the relative atomic mass than a rarer isotope. We can define relative atomic mass as being the average mass of one atom of that element compared to 1/12 of the mass of one atom of carbon-12. You can also use the same definition substituting in mole instead of atom, as long as you're being consistent with yourself within the definition. There are a few different types of calculation that you might be asked to do with respect to relative atomic mass. The first one is our vanilla GCSE work out what is the relative atomic mass. So here we're given a couple of different isotopes and their relative abundances, and then we're just trying to work out an overall AR. So for each one of those isotopes, you're going to multiply the mass by the abundance, and then you're going to divide it by the total abundance. Now here, because this is percentage abundance, it actually adds up to 100, and this makes it a really simple calculation, but as we're going to see in a second, it's not always going to be percentage abundance data. It's always worth, when you do one of these calculations, having a little check at the end and saying, that answer there, is it sensible? So is it between 16 and 18? Yes. And is it closer to the more abundant isotope? Also yes. The second type of calculation would be where we're given abundance data that doesn't add up to 100. So here we can do this in exactly the same way that we just did. The difference is that the previous question we could have chosen to use decimals if we wanted to, but here we can't. So what I want to watch out for here is that the denominator of my fraction here is going to be 32. It's not going to be 100. And this is something that people often come unstuck with if they're just used to always dividing by 100. So again, I can do a common sense check. Yes, this answer is between 14 and 15. And yes, it's closer to the more abundant isotope. Then our third possibility is where, rather than being given the isotopes and the abundances, we're given the relative atomic mass and asked to work out backwards from there. So the first thing we're going to do is to write an expression for what relative atomic mass is, substituting in the numbers that we've got. And here I'm using X as the mass of the isotope because I don't know what it is. So if I then simplify all that and expand out my brackets, I get these. And if I pull all the like terms over onto one side, I get a value for 8x. And then if I divide by 8, I'm going to get an answer of almost exactly 13. Now here I don't have an integer number, but what I know is that the mass of the isotope must be an integer. So if you're calculating what the missing isotope is, you're always going to round your answer. To generate the abundance data that allows us to calculate relative atomic mass, we need to use mass spec. And for AQA AS-Chemistry, all you need to know about is time of flight mass spectrometry, not any of the other versions. So mass spec is an analytical technique and it allows us to measure the mass to charge ratio of ions. But since the vast majority of those ions are only going to have a single positive charge, this is really basically just going to give us the mass. So you need to be able to talk through the 5 steps of mass spec. The first step in mass spec is ionization, and depending on the kind of substance that you're trying to analyse, you might use one of 2 different methods. If we've got a large organic molecule that could fragment easily, then we're more likely to use electrospray ionization. And this is where the substance is dissolved in probably some water or some methanol, something that's polar and also volatile. And then it's injected through a needle that's attached to a high voltage power supply. And it needs to be voltage, not anything else. In that process, each molecule is going to gain a proton, and that's going to mean that your final ion has a positive charge and it's also 1 atomic mass unit heavier than the original molecule. So say if we were analysing decane, it's got an MR of 142, the final ion would have an MR of 143. Then alternatively, we can use electron impact, and this is where we use an electron gun to fire high energy electrons, and those electrons knock another electron off the original substance, and therefore the mass of that ion is the same as the mass of the original molecule or atom or whatever, but it has this positive charge now because it's lost 1 electron. Next, all of those ions are going to be accelerated, and this is done by them being attracted to the negative plate because of course they all have a positive charge. Then they're going to travel through the drift chamber, and that's how they're all going to end up spreading out. And then they're going to be detected when they hit this negative plate and they pick up an electron, and this causes a current to flow. And then the size of that current is going to be directly proportional to the abundance of that ion. So if there are twice as many of the ion, we'll see twice as large a current flowing. It's very likely that if you have a question on mass spec, you'll get 5 or so marks at the end where you have to do some kind of calculation, and that could be working out the length of the flight tube, the length of time that it takes for a particular ion to move, what other ion there is if they give you the data for one isotope. In those questions, they will give you the equation for kinetic energy that you used to have to memorise for GCSE physics, but they'll only give it to you in the original form. So it's worth, if you're not very good at rearranging it, learning the rearranged version with V as the subject. Watch out for the fact that in order to be used in that calculation, the mass needs to be in kilograms, even though you're used to having masses in grams for masses Mr. Mole type things. And also be aware that you do need to know how to calculate velocity. So velocity is going to be distance divided by time. Rather than being given numerical data, you could be given a mass spec readout to interpret. Watch out again that these could be abundance values rather than relative abundance values, so they might not add up to 100. But if they are relative abundance values, then you can speed up your calculations by just using decimals rather than using the fraction method. Where you have an atom that has more than one stable isotope, this can also lead to some funky mass spec data in terms of molecules. So say chlorine is a divalent molecule, forms Cl2, and we know that 3/4 of all the chlorine in the world has a mass of 35. So on that basis, you'd say that if you pick a particular atom of chlorine, you've got a 3 in 4 chance that it's chlorine 35. And if we pick 2 different atoms, then the chance of that happening twice is going to be 9/16. So the chances that we have a chlorine 35 molecule is 9/16 of the total. And then likewise, the chances that we pick chlorine 37 twice is going to be 1/16. And you'd have the 6 remaining 16ths are that sort of hybrid molecule where it has one of each. Then we move on to electron configuration. So you should know that electrons occupy fixed energy levels, which we call shells, just like we did at GCSE. And the shells can now be further divided into subshells called S, P, D and F, the same as the blocks of the periodic table. And then each one of those can be split up into one or more orbitals. And an orbital is just an area of space where there's a high chance of us finding an electron. And all of the orbitals have room for 2 electrons in them. So we've got 1 s orbital per subshell, we've got 3 p orbitals, and then 5 d orbitals, and so on. In any given energy level, the s orbitals are the lowest energy level, so we can have questions later about how easy it is to lose electrons, and we're always referring to the fact that, say, a p orbital is higher energy than an s orbital, and those orbitals also have characteristic shapes. There are 3 key principles for arranging electrons in atoms. The first one is that we always work from the lowest energy to the highest energy. So for instance, we always put things in s subshells before we put them in p subshells. The second one is that within any particular orbital, 1 electron spins up and 1 electron spins down. And the third rule is that we don't start pairing electrons in orbitals as long as there are other orbitals free in the same energy level. So we're going to fill them up separately, and then once they're all full, then we can start pairing. So our first electron in hydrogen is easy, and then in helium we pair. We don't carry on to another one because the 2s subshell is a higher energy one than the 1s subshell, so therefore we're allowed to pair. Then lithium, we go 1 up, 1 down, and we start the new subshell. Then beryllium, we again have to pair because 2p would be higher energy than 2s. Then with boron, we're finally allowed to start using that 2p subshell, and then when we get to carbon, we don't pair that 6th electron because there's still another orbital which is the same energy as the first 2p orbital. And then likewise for nitrogen, we're still not pairing. It's only when we get to oxygen that we start to pair those electrons. There are a couple of little things that might trip you up. The first one is that despite being part of the 4th shell, the 4s orbital is lower energy than the 3d orbital, at least when it's empty. And so therefore we're going to put electrons in there before we put them into 3d. However, the presence of electrons in that orbital change its energy level. And so that means that although it's lower energy than 3d and therefore fills first, once it's filled, it becomes higher energy than 3d and therefore it will also empty first. So if you're doing the electron configuration for a titanium atom, then we would have 4s2, 3d2. I'm just using the noble gas configuration here in order to save time. But then when it comes to a titanium 3+ ion, it's going to lose those 2 electrons out of 4s before it starts losing from 3d. So it's still left with 1 in 3d. I wouldn't write the 4s0 bit here. I'm kind of putting it in so that you can see that they've been removed from there. Then the other rule that might trip you up is what I refer to as the copper or chromium rule, because these are the 2 elements that you're most likely going to encounter it with. So we know that atoms are more stable when either all of their d orbitals are full or all of their d orbitals are half full. So in other words, having 3d5 or 3d10 is much more stable than 3d4 or 3d9. And therefore, for instance, when we get to nickel, we would have 3d8 4s2 because that 4s has filled first. But then when we get to copper, we kind of take one of those electrons back from 4s and use it to top up the 3d so that we actually get to 3d10 rather than 3d9. You should be able to define that the first ionisation energy of any particular atom is going to be the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of that element to make 1 mole of gaseous ions. So it's really important when you write an equation for this that you're including the state symbols. That's the number one thing that people miss out and lose the mark on. It's also worth us just emphasising that it doesn't matter what the element is. It doesn't matter if in chemical reactions it forms negative ions or if it forms 2+ ions. First ionisation energy is always about removing an electron to make a single positive ion. You need to be able to explain why we see variation in first ionisation energy across the periodic table. So the first thing is that there's a general trend that as you move from left to right, we see an increase in first ionisation energy. And the reason for that is the increased nuclear charge. As we go left to right, each element gains 1 more proton, and therefore there's a stronger electrostatic force of attraction between the nucleus and the outer shell electrons, and that means it takes more energy in order to remove that outer shell electron. The second thing that we see is a drop in first ionisation energy as we start either a new subshell or a new shell. And the reason for these is that these electrons are in higher energy subshells or shells, and therefore they're experiencing more shielding and they're further away from the nucleus and they're more easily lost. The third thing that we see is that when we get to oxygen and when we get to sulfur, again, there's a drop. And the reason here is that the electrons are now being paired for the first time. And so the paired electrons are repelling each other more strongly than unpaired electrons would do. And therefore, that is decreasing the amount of energy needed to remove that electron. The second topic is the amount of substance topic, and we start off with the mole and the Avogadro constant. You should know that the Avogadro constant represents the number of particles in a mole, and that could be atoms, molecules, ions, electrons, literally anything. In all your calculations where you're using this number and where you're doing quantitative chemistry in general, you should be giving your answer to an appropriate number of significant figures. And you can work that out by looking at the numbers used in the question, and whatever the smallest number of significant figures used is, that's the number that you want to round to. At A-level, we no longer talk about concentrations in terms of grams per decimetre cubed, and we exclusively use moles per decimetre cubed, but you still could be given mass data and expected to use masses Mr. Mole to convert to moles in order to be able to calculate a concentration. The ideal gas equation is everybody's favourite equation because it's quite straightforward to recall, and often that in and of itself is worth a single mark, and then rearranging it can be worth a second mark. But in contrast to that, you sometimes have to do 3 different unit conversions in order to get the mark for that bit. So just make sure that you're aware that pressure needs to be in pascals, so you're going to need to multiply it by 1,000. Volume is in meters cubed, so you often need to multiply it by 1,000,000, and temperature needs to be in Kelvin, so you may need to add 273 to a temperature that's been given to you in Celsius. The ideal gas constant will be given to you in the question. Empirical formula is the simplest whole number ratio of atoms of each element in a compound. So when we think about ionic compounds, all of their formulae are empirical formulae. But for a molecular substance, it may or may not be the same thing. So for instance, all alkenes have an empirical formula of CH2. To calculate empirical formulae from mass data, we're going to start off by using masses Mr. Mole to work out how many moles of each element we have. You rearrange your equation, and then we work out that we've got 0.3 moles of nitrogen and 0.6 moles of oxygen. Then we put those together in a ratio, and then we need to convert this to the simplest whole number ratio, which we do by dividing by the smaller of the two numbers. So here I divide the left side by 0.3 and then the right side by 0.3. Don't fall into the trap of dividing both sides by themselves, because then you'll just get 1 to 1. This gives me an answer of 1 to 2, and then I need to express my answer as an actual formula, not just leave it as a ratio. So my final answer here would be NO2. If you're still not feeling super confident balancing equations, start off by counting up the number of atoms of each type you have on each side. Then, for one of your elements that's unbalanced, look for the lowest common multiple and think about what you need to multiply each side by to achieve that. So here I'm going to start with carbon. The lowest common multiple of 1 and 7 is 7. So I need to do nothing on the left, and I need to multiply the right-hand side by 7. So I add that coefficient in there. And then I need to make sure that I've added up everything else that's changed. The oxygen changed, and I changed that as well. So then I'm going to look at my hydrogen, and I'm going to need to add 3 of those. And then for my oxygen, I've got 17 in total on the right-hand side. So I'm going to need 17 on the left-hand side, but I need to take account of the 2 that are in this carboxylic acid. So I remove those, I'm left with 15, and therefore I need to add 7.5 as a coefficient for oxygen. It's really likely that you're going to see some kind of theoretical yield type question. So remember, start off by doing your housework. So remove anything that's not part of the question that you haven't been asked to calculate, and then write down what the MR for each substance is. Then you're going to calculate the number of moles of the substance that you do have the mass of, because remember, working out the number of moles is almost always worth a mark. So here I've got 0.5 moles of the sodium azide. Then I need to look at the coefficients to work out how many moles I have of the second substance, and this is probably the most common thing that students leave out when they're doing these calculations. So you divide by the coefficient of the thing you already know about, you multiply by the coefficient of the thing you're trying to work out. So I've got 0.75 moles of nitrogen, and then I go back to masses Mr. Mole to work out that I've got 21 grams. Atom economy is a measure of what proportion of the reactants that I started with actually ended up in my useful product, as opposed to in a byproduct that I can't use. Having a reaction with a high atom economy is desirable because it's going to save me money, it's going to mean that resources are being preserved, and it's probably going to save energy as well and generally be better for the environment. It's highly likely that you have to write a balanced simple equation for a reaction where you haven't been given the formulae of all of the products, so you need to be able to work these out. You should know from GCSE how to work out the charges of any monatomic ions, but then you're also expected to recall some compound ions, both what their formula is and also what the charge on them is. So that's ammonium ions, sulfate, carbonate, nitrate and hydroxide. Phosphate isn't actually on the list of ones you're expected to recall, but particularly if you have reactions with phosphoric acid, it's useful for you to know that it exists and that it has a 3- charge. Now, for any of these, remember, if we're making an overall compound, it needs to have overall no charge. So what you need to do is look for a way to make the positives and negatives balance, and we do that by looking for the lowest common multiple. So say if I picked aluminium sulfate, the lowest common multiple of that 3+ and that 2- is going to be 6. So I then think, well, how do I get 6 positives and how do I get 6 negatives? Well, the aluminium, we're going to need 2 of them, and the sulfates, we're going to need 3 of them, and so we then put those together in a formula like this. And remember to use brackets around your compound ions. As well as needing to write balanced symbol equations for reactions, you may be asked to write ionic equations and half equations. We'll look at half equations in more detail when we get to the redox topic, but remember that for an ionic equation, what you want to do is start out with your simple equation, then take any ionic substances and break them down into the ions that make them up. So here that would be the iron ions and the chloride ions, and then the magnesium ions and the chloride ions. And if something doesn't change between the left side and the right side, if its oxidation state remains the same, then you remove it. It's a spectator ion and it doesn't need to be included in the ionic equation. In the first part of the first required practical, you make a standard solution. Now, it's possible that you get this as a slightly calculation-y question, where you're given a particular volume and concentration and you need to calculate what mass of the starting substance you're going to need. Now, in terms of the method, the first thing that we need to do is to weigh out the precise amount that we need, and we need to actually know what's been added to the solution, not just what we weighed out initially. So either you're going to do the weighing before and after method, or you're going to make sure that you rinse everything into the beaker that you're using to dissolve it in. Then you're going to dissolve that using some distilled water, stirring it with a glass rod to make sure that everything dissolves nicely, and then transfer it to a volumetric flask using a funnel. You need to make sure that you've rinsed down all of the glassware that you're using and that all of those rinsings actually go into the volumetric flask. Then you're going to add more distilled water until you've got the meniscus resting just on the calibration line, and you may need to use a dropping pipette in order to do that accurately. And then finally, you're going to stopper your volumetric flask and invert it several times in order to homogenise the solution. So it's really important that that inversion or that shaking happens right at the end. It's not something that you're doing to make things dissolve earlier on. In the second part of the required practical, you're carrying out a titration in order to work out the concentration of an unknown substance, which is what's going to go in your conical flask. Before you get started, you need to rinse through your burette, but you can't do this with water because doing that would change the concentration of the solution that you're putting into the burette. So instead, you rinse the burette with the solution that will be eventually going into it. So if you're putting sodium hydroxide in your burette, you rinse it through with sodium hydroxide, and this will remove impurities and also allow you to fill up that jet space at the bottom. The substance that you don't know the concentration of goes into the conical flask to allow you to swirl it without it splashing out, and you measure that using a volumetric pipette. You also need to include an indicator like phenolphthalein or methyl orange, and these are good indicators because they have very clear, distinct colour changes. And so you're going to titrate until you see the first permanent colour change, and then you're going to repeat that process until you get concordant data, which are titers that are within 0.1 centimetres cubed of each other. We often use a white tile underneath the conical flask in order to allow you to see the colour change more clearly. You need to make sure that you're measuring all of your volumes at eye level, looking at where the meniscus lies, and your most accurate concentration is going to be calculated when your burette contains a very dilute solution, because this is going to mean that the volume that you add is larger and therefore the percentage uncertainty is smaller. You use a wash bottle to rinse down the sides of the conical flask and the outside of the burette because we want to make sure that anything that's coming out of the burette is actually ending up in the chemical reaction and not just stuck to the sides of the glassware. And it's fine for us to do this because when we work out the final concentration, we're going to use the volume of 25 centimetres cubed that we originally put in there. We're not actually going to use the volume that ends up in the conical flask. So even though you're adding water, you're not changing that volume that you're using for the calculation, so it doesn't matter. You may also encounter a quantitative question where you have to complete a calculation that is a back titration. So back titration is what we use when we're trying to assess the percentage purity of a substance that is a solid. So you can't titrate with it directly. So what you do is, for instance, you take some acid and you react the acid with your solid. Then you take the leftover acidy goodness and you use that in a titration with, say, some sodium hydroxide. And what you do is you compare the number of moles of acid that you started with the number of moles of acid that the titration tells you that you have. And then the difference between those two numbers is the number of moles of acid that reacted with your solid, and this allows you to complete your percentage purity calculation. In the bonding topic, we talk about 4 different kinds of crystal structure. So crystal structure just means what is the overall structure of this substance? Is it ionic like sodium chloride? Is it metallic like magnesium? Is it macromolecular, which you would have called giant covalent at GCSE, like diamond and graphite? Or is it a simple molecular substance like ice? Unlike at GCSE, where we made distinctions between bonding types based on whether things were metals or non-metals, at A-level we appreciate that it's a bit more nuanced, and really we're talking about differences in electronegativity. So if we have elements that have a large difference in electronegativity, then they experience ionic bonding, and this involves electrostatic attraction between the oppositely charged ions in a giant ionic lattice. These substances are solid at room temperature because that strong electrostatic force of attraction requires such a huge amount of energy to overcome, and it's likely that you might be asked to compare and contrast an ionic substance with a covalent substance, and the idea that if we've got stronger forces it takes more energy to overcome, so therefore we have a higher melting or boiling point. You could also discuss the fact that ionic substances can only conduct electricity when they're molten or aqueous, and the reason for that is that even though they have charged particles, i.e. ions, in a solid, they're not free to move. You definitely don't want to be mentioning delocalized electrons anywhere in a question about ionic bonding. You know from GCSE that a single covalent bond is a shared pair of electrons, where a double covalent bond contains 2 shared pairs and a triple covalent bond contains 3 shared pairs of electrons. You also learned in Year 12 that a coordinate or dative covalent bond is one that contains a shared pair of electrons with both of the electrons supplied by one atom. So for instance, the ammonium ion is produced when an ammonia molecule with a lone pair on the nitrogen is able to donate that lone pair to a proton that it picks up from a solution to make the ammonium ion. And you might also have encountered dialuminium hexachloride, which is made when one aluminium chloride molecule and another aluminium chloride molecule are joined together by 2 coordinate bonds. And that's a perfect example of where at GCSE we would have expected a metal and a non-metal to make an ionic bond, but actually here we see covalent bonding. Also, don't forget your giant covalent substances and that they contain thousands and thousands of atoms. So this is going to include your diamond, which makes 4 strong covalent bonds per carbon atom. But remember, there are thousands of those carbon atoms, so therefore melting it is incredibly difficult and needs a lot of energy. And likewise, your graphite also contains thousands of atoms, but crucially, it's made of these hexagonal layers, or planes is what we tend to say at A-level, which are able to slide over each other because there are no strong covalent bonds between the layers. Metals consist of a giant metallic lattice, which is made up of regular rows of positive ions and a sea of delocalized electrons. If you're asked to draw this, you need to make sure that you're drawing at least 6 ions. There's then a strong electrostatic force of attraction between those positive ions and the delocalized electrons. Metals are able to conduct electricity because these electrons are delocalized, and therefore they're free to move and carry charge through the metal. In a question about properties, the first thing you want to ask yourself is this comparative or is it about one substance? If you're asked why does A have a higher melting point than B, then you need to be talking in terms of it taking more energy to overcome the forces. But if you're just asked why does A have a high melting point, then you need to be saying it takes a lot of energy to overcome those forces. It sounds like a really pernickety thing, but it will cost you marks in the exam. The second thing you want to think about is what are those forces being overcome, which may not be the same thing as what type of bonding it has. If it's an ionic substance, then obviously it's a strong electrostatic force of attraction being overcome. But if it's a covalent substance, you need to think, is this a giant covalent structure, a macromolecule, in which case the covalent bonds are being broken, or more likely, are they asking you about a simple molecular substance, in which case it's the weak intermolecular forces that are being overcome. So if I have 2 methane molecules here, and I'm looking at why does methane have such a low boiling point, it's because this weak intermolecular force is being overcome. It's not the strong covalent bonds inside the molecule that are breaking. Then, if you're asked about electrical conductivity, you need to think, does this substance have charged particles and what are they? Please don't write about delocalized electrons if the question asks you about ionic substances. And then secondly, are those charged particles free to move? So this is where we think about the fact that ionic substances can't conduct electricity unless they've either been melted or dissolved. We can think about electrons as charge clouds that repel each other, and in trying to get as far apart as possible, they cause molecules to have different shapes. Remember, it's always the electrons that are repelling each other, not the atoms that they're attached to. When you're trying to decide what to call a particular shape, firstly you need to consider all of the electrons regardless of whether they're lone pairs or bonding pairs, and that number of electrons is going to give you your basic shape. And then particularly for tetrahedral molecules, you're going to actually name the shape based on the bonding pairs only. Linear molecules are going to have a bond angle of 180, and watch out because this one often comes up where you have something that has lots of extra lone pairs, but when you're naming it, it's just linear because it only has 2 bonding pairs. Then we have trigonal planar where we have a bond angle of 120, and your basic tetrahedral with a bond angle of 109.5. Trigonal bipyramidal has 2 different bond angles. So we have 2 bonding pairs that are as far apart from each other as they can be, kind of top and bottom, and there's a 90-degree angle between them and the 3 remaining bonding pairs, which are all sort of forming a 2-2 around the middle, and the angle between them is 120, just like in the trigonal planar molecule. Then we have our octahedral molecule, which confusingly only has 6 bonding pairs of electrons because it's based on 8 faces of the 3D shape, and that has bond angles of 90 degrees. Then we need to think about our alternative tetrahedral shapes. So if we have 1 lone pair, then this is going to reduce the bond angle by 2.5 degrees, and we're going to call that triangular pyramidal or just pyramidal. And then we also have our bent or nonlinear molecule like water, which has 2 lone pairs, so we remove 2 sets of 2.5 degrees to have a bond angle of 104.5. And the reason for that is because the lone pairs of electrons are going to repel each other more than the bonding pairs of electrons. In order for us to describe differences in intermolecular forces, we need to be able to talk about bond polarity. So firstly, we can define electronegativity as being the power of an atom to attract the pair of electrons towards it in a covalent bond. So I could say that fluorine is more electronegative than chlorine because it has fewer shells, so there's a stronger attraction between the nucleus and the bonding electrons. Remember, it's those bonding electrons, not just generic outer shell electrons. Now, when atoms differ in electronegativity, that will cause the covalent bond between them to become polar, and it's possible that this may lead the whole molecule to become polar if the molecule is not symmetrical. So if you look at my diagrams on the right hand side here, I have chloromethane with this one polar bond, and so we're going to have a delta negative on the chlorine to show that that's the more electronegative atom, and the delta positive on the carbon at the other end, and that would have a permanent dipole interaction between other molecules of the same type. But if you look below that at the tetrachloromethane that I've drawn, even though those individual bonds are polar bonds, because the molecule is symmetrical, they sort of cancel each other out, and we don't have a permanent dipole force between the molecules, because just the whole of the outside of that molecule is these slightly negative chlorines. You need to know about 3 different types of weak intermolecular force, but before we go into them, you need to understand that the strength of these forces have overlapping ranges. So it's not the case that every single molecule that has hydrogen bonds between its molecules is going to have a higher boiling point than every single molecule with van der Waals forces. Something with very strong van der Waals forces could have stronger intermolecular forces than something with very weak hydrogen bonds. So say if you consider a really big polymer that's not polar, it just has van der Waals forces, but because it's so big and has so many electrons, those van der Waals forces are stronger than the hydrogen bonds that we see between water molecules. So our first and strongest type of weak intermolecular force are these hydrogen bonds, and there are 2 crucial things you need to understand. The first one is a reminder that it is a weak intermolecular force. So when we talk about hydrogen bonds breaking, we mean the forces between molecules. We don't mean the strong covalent bonds inside the molecules. The second thing is that this whole process arises because of the difference in polarity between hydrogen and 3 key atoms, fluorine, oxygen and nitrogen. So in order for hydrogen bonding to arise between 2 molecules, they need to contain bonds that are polar bonds between hydrogen and fluorine, oxygen or nitrogen. It's not good enough for a molecule just to have some fluorine and some hydrogen if they're not bonded to each other. Our second type of weak intermolecular force is the permanent dipole interaction. This is going to arise when we have a non-symmetrical molecule that contains bonds that are polar but not as polar as the ones that lead to hydrogen bonding. So for instance, if you have carbon bonded to chlorine, that's a polar bond, and if it's a non-symmetrical molecule, that could lead to a permanent dipole interaction between 2 adjacent molecules. Then your final type of weak intermolecular force is the van der Waals force, and this is going to arise because of the random distribution of electrons around a molecule. So the larger a molecule is, the more electrons it has, and the more likely it is that just by random chance there's an unequal distribution leading to a temporary dipole on one molecule. And this is then going to induce a dipole on an adjacent molecule, and then the attraction between the positive end of one molecule and the negative end of the other molecule is going to lead to that van der Waals force. So the larger a molecule is, the more likely it is that this arises, and the stronger van der Waals forces that molecule experiences. Chemical reactions can be endothermic, in which case overall they absorb energy from the surroundings and therefore lower the temperature, or exothermic, in which case overall they give out energy to the surroundings and increase the temperature. Delta H is the symbol used to denote an enthalpy change, which is a heat energy change measured under conditions of constant pressure. If the value of delta H is negative, then the reaction is exothermic, and if it's positive, then the reaction is endothermic. We measure standard enthalpy changes at 100 kilopascals and a stated temperature, which is usually 298 Kelvin, but could be a different temperature if that's what's stated. You need to define the standard enthalpy of formation as the enthalpy change, or we would accept the heat energy change, when 1 mole of a substance is formed from its constituent elements under standard conditions and with all reactants and products being in their standard states. It's important that you're saying all reactants and products, not just everything. Then the standard molar enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in oxygen, or in other words, burned in excess oxygen, again with all reactants and products being in their standard states. We don't have to include the line here about standard conditions, because when you're setting fire to something, it's not going to be standard conditions because the temperature is going to change. It's very likely that you're asked to calculate a standard enthalpy from some experimental data, and the first step in this is going to be working out how much energy is absorbed or more likely released, and for this we use the formula Q equals mc delta T. Now in this formula m is mass, but crucially it's the mass of whatever is changing temperature. So if you're doing, say, some flame calorimetry, you're burning a fuel and you're heating up some water, it's the mass of the water, not the mass of the fuel. Then C is the specific heat capacity, which you're going to be given in the question, and T is the change in temperature. And because it's a change in temperature, it doesn't matter if the temperature is measured in degrees C or in Kelvin. You don't need to convert because the change will be the same. For the second required practical, you needed to measure an enthalpy change, and the one that the exam board recommend is dissolving copper sulfate. So we do this reaction in a polystyrene cup in order to minimise energy losses to the environment. And before you start, it's really important that you take the temperature at regular intervals for a long enough time, usually 4 or 5 minutes. And this is to establish an accurate starting temperature and to make sure that the temperature of that water wasn't changing before you did anything to it. Then we need to dissolve the copper sulfate in this, and it's really important here that we have to use the before and after weighing method. You can't use the rinsing method because in order for us to calculate an accurate enthalpy change, we need to have a known mass of water and it all needs to be interacting at the same time, so you can't use that rinsing. So you weigh your weighing boat with your copper sulfate in, then you pour it out and you weigh that weighing boat afterwards to see how much was actually transferred, because there may be residue. You measure the temperature over several minutes, maybe up to 15 minutes, and then you plot the temperature against the time, and you're going to draw 2 lines of best fit. So one for your initial readings where there was just the water, and then one for after you added the copper sulfate. And then what you do is you extrapolate both of those lines until the point at which you added the copper sulfate, and the difference between them will be the temperature change. You can then use that information together with the Q equals mc delta T calculation, remembering of course that the m, the mass, is the mass of the water, not the mass of the copper sulfate. What you need the mass of the copper sulfate for is calculating the overall enthalpy change. So you take your value for Q, which is in joules, you divide it by 1000 to put it into kilojoules, which is what we're going to need for delta H, and then delta H is in kilojoules per mole, so you then need to use the mass of copper sulfate that you added together with the MR to work out the moles, and you divide your Q, which has been converted to kilojoules, by the moles to get kilojoules per mole. Hess's law tells us that the enthalpy change for a reaction is independent of the route taken. For questions that ask you to work out an overall enthalpy change, I would always draw a Hess's cycle because it's much easier to pick up working marks for a properly drawn cycle than it is for a mathematical expression. The first thing you should do is look at your table of enthalpy change data and decide, is it combustion data or formation data, and then write an equation for each one of these processes. So here we've got the combustion of carbon and we've also got the combustion of carbon monoxide. Now that I've written those expressions, this is going to tell me which way my arrows need to go. So here I'm making carbon dioxide and I can add in my 2 arrows and I know which way they're going to go because I can look at the equations I've already written. Then I can add numbers onto those arrows. Watch out for the fact that you may have more than 1 mole of a particular substance, in which case you would need to multiply these values. Then I'm going to write start and end on either end of the arrow that I'm trying to work out the value of, and draw a new arrow that goes from start to end, but going the whole of the rest of the way around the cycle. This is going to help me to see, am I going the right way up arrows or the wrong way up arrows? So I'm going the right way down the -393 arrow, so I keep that number as it is, but I'm going the wrong way up the -283 arrow, so therefore I need to flip the sign or just add another minus number, and then I can work out that the overall enthalpy change is -110 kilojoules per mole. There isn't actually one gold standard value for how much energy it takes to break a carbon-oxygen bond or a nitrogen-hydrogen bond. It depends upon the context of the rest of the molecule and what else is going on. So when we define mean bond enthalpy, this is the amount of energy required to break 1 mole of the stated bond, because it's a standard enthalpy change, but it's averaged across a range of compounds that contain that bond, because it will be different. And this means that when you compare experimental data to a databook value, then you might have slight differences because of that. In terms of calculation, your most straightforward is working out the energy change for a reaction based upon some bond enthalpy data. So we would add up all of the bonds that are going to be broken and subtract from that all of the bonds that are going to be made, and the difference between those two numbers is the overall enthalpy change. If it's negative, that shows you that the reaction is exothermic, and if it's positive, then it's endothermic. For A-level chemistry, it's much more likely that you get a situation where you're told what the overall energy change is and you need to work backwards to figure out the value of a particular bond. I'd really strongly suggest that you actually do a quick sketch of the different molecules, because this means that you can cross out the bonds as you include them in your calculation, and it saves a situation where you have a coefficient and you don't remember to double up or triple up all of the bonds in that molecule. So here we're going to write ourselves an expression for all the bonds on the left take away all the bonds on the right. If you've got a reaction, particularly with organic molecules, you might have a whole load of bonds that don't need breaking, say lots of carbon hydrogens, and it's up to you whether you want to include those on both sides of the equation or not. Both calculations will be in the mark scheme. Once we've written out this expression, we can start to simplify it. Make sure that you've got extra brackets around everything on the right hand side, because very commonly people will take away that first set of bonds and not the 4x. And then we simplify this down further. And one thing that's worth pointing out is that the final mark of this calculation is always for finding one of the bond. So even if you have a complete brain melt and you can't remember how to get through the rest of the calculation, if you've done some kind of calculating and then you divide by the appropriate number, you can still pick up a mark there. The kinetics topic isn't included in paper 1 of AQA AS-Chemistry, so we move straight on to equilibrium and Le Chatelier's principle. This is going to apply to reversible reactions, and you're going to know it's a reversible reaction because it's got that reversible reaction arrow. We know that at equilibrium, the forward and reverse reactions are proceeding at equal rates, and this means that the concentration of the reactants and the products remains constant. Crucially, constant means it's staying the same. It does not mean that they are equal to each other. We can use Le Chatelier's principle to make predictions about the effect if we change the temperature, the pressure, or the concentration. It's really important that in the first line of your answer, you're talking about the system shifting to counteract the change. But unlike at GCSE, where that statement on its own would be enough, you need to make sure that you're including what the change is. So for instance, saying the system shifts to counteract the increase in temperature. Next in your answer, you want to include which reaction, forward or reverse, is being favoured and why that's the case. So for instance, we might favour the endothermic reaction because we're trying to reduce the temperature after a temperature increase, or we might favour the side which has fewer molecules on because we're trying to reduce the pressure after it's been increased. Finally, you need to make sure that you're talking about which side does the equilibrium move to. So if you're favouring the forward reaction, it's moving right. If you're favouring the reverse reaction, it's moving left, and what the impact on the yield will be as a result. Remember, adding a catalyst is not going to affect the position of equilibrium, so it's not going to affect how much product you make. The reason for this is that the forward and the reverse reactions are both going to be sped up by the same amount. What the catalyst will do is it will make the reaction happen faster, so it will reach equilibrium sooner, but the overall concentration of the product will be the same as it was before. You should also know that when we're thinking about industrial processes, we might need to make a compromise between the temperature and the pressure. So for instance, the Haber process is an exothermic forward reaction, and that means that raising the temperature would make less yield, but if we have the temperature too cold, then the reaction really slows down, and so we have to pick a compromise temperature. Next, we move on to the equilibrium constant Kc. Where we say homogeneous systems, this means that everything is in the same phase, so either everything is a gas or everything is a solution. The first thing you need to be able to do is to write an expression for Kc. So here we're using concentration, which we show using square brackets. The products go on the top of the expression and the reactants make the denominator. And then the coefficients in the symbol equation are going to become the powers in that expression. In order to work out the units, we start from the base unit of moles per decimetre cubed because all these concentrations are going to be measured in these. You could choose to write it out for every single thing in the expression and then cancel them out, or if you look at your symbol equation, look at how many moles you have on either side. So here we've gone from 4 moles on the left to 1 on the right, so we've gone down by 1, so -1. And I'm then going to take moles per decimetre cubed and put that to the power of -1. If I expand those brackets, I end up with moles to the -1 decimetres cubed, and those are my final units. The number one mistake that we see from students with KC expression calculations is that they calculate things in terms of moles and then forget that we need concentrations to go into the KC calculation. So you need to take your moles and divide each one by the total volume, and that's going to give you concentration. The one time that they might not give you volume is if you have equal numbers of moles on the left and right side of your equation, then all of those volumes are going to end up cancelling out, and then you would be able to complete the calculation without reference to volume. Often, before we can substitute numbers into a KC expression, you're going to need to calculate the number of moles and therefore the concentration. And the easiest way to do this is to draw what we call an ICE table. So we have initial moles, change in moles, and then end moles. So in this question, we're told that we start with 2 moles of A and we finish with 1.7. So that's a change of going down by 0.3. Then if I look at my equation, I can see that for every 1 mole of A, I'm using 3 moles of B. So I'm going to use up 0.9 moles of B and be left with 0.1. Then A and C are in a 1-to-1 ratio, so if I've used up 0.3 of A, I'm going to make 0.3 of C, and I've got twice as much D, so I'm going to be making 0.6 of D. So I'm left with 0.3 moles of C and 0.6 moles of D. Then my final step is that I need to take each one of those sets of moles and I need to convert it to a concentration by doing the moles divided by the volume. Your final physical chemistry topic for this paper is redox reactions. So you know from GCSE, you've remembered that oil rig is a thing, so oxidation is loss of electrons and reduction is gain of electrons. But we now learn in year 12 that oxidizing agents oxidize other species by accepting their electrons, and reducing agents reduce other species by donating their electrons. Oxidation states are a numerical way of representing how electrons move within redox reactions. In order to work out the oxidation state of any element within any compound, there are a certain set of rules that you need to have memorised. The first one is that elements always have an oxidation state of 0. From there on, we're always working from most electronegative to least electronegative. So say if you have some fluorine and some oxygen and you can't satisfy both of their rules, the fluorine wins because fluorine is the most electronegative element. So fluorine will always have an oxidation state of -1 when it's in a compound. Obviously when it's F2, it's 0. Then oxygen will always be -2 unless it's either bonded to fluorine, in which case that rule takes precedence, or it's in a peroxide where it has an oxidation state of just -1. Chlorine will also have an oxidation state of -1 unless it's bonded to something more electronegative, in which case that rule takes precedence. Hydrogen will always be +1 unless it's in a metal hydride, in which case it's -1. And group 1 metals are always +1, group 2 metals are always +2. Transition metals, we're going to look at the charge of the monatomic ion, so you look at the Roman numerals and so on. Unlike in a symbol equation or an ionic equation, for a half equation we're only interested in one particular element, although we are going to have to include hydrogen and oxygen in our half equation to make it work out. So your first step is to identify which element is changing oxidation state and make sure that that element is balanced. Now here it already is, but particularly if you're working with a non-metal, you could have something like this chloride ion being discharged to make chlorine molecules, and there we would need to include a coefficient of a 2 to make chlorines balance. My next step is to add water molecules to make the oxygen balance. So I've got 4 oxygens in the manganate ion, so I add 4 water molecules on the right hand side. But in doing that, I haven't just added 4 oxygens, I've also added 8 hydrogens, so I have to put those back on the left. And then I want to think about the charges. So here on the left, I've got a minus and 8 pluses, which makes a total of 7 plus. I've got the 2 plus on the manganese on the right hand side, and so I'm going to need to add 5 electrons to the left. You might also have been taught to do electrons as the second step. That's certainly how I used to teach it. So if we look at the oxidation states, we go from +7 on the left to +2 on the right, and that would also lead us to add 5 electrons. If you're going to combine 2 half equations, then you need to have the same number of electrons overall. So here I've got 5 in my left-hand equation and 2 in my right-hand equation. So the lowest common multiple of those would be 10, and so I'm going to take this first equation and times it by 2, and the second equation and times it by 5. This then gives me these equations, and now I'm able to cancel out the electrons, but I'm also able to cancel out some of the hydrogen ions. So I can cross out the 10 and I can replace my 16 with just 6. And now I'm able to join those two equations together to produce an overall equation that looks like this. Thank you very much for watching, and I hope you're now feeling slightly calmer and more prepared for tomorrow's AS Chemistry exam. Don't forget there is also a part 2 of this video which contains all of the inorganic chemistry that is in AQA AS Chemistry paper 1.